Hi everyone, here's the second part to our chapter 13. Let's look at energy changes in solution formation. What happened to the energy? Okay. Step 1. Solute particles first need to separate from each other. This process is endothermic, meaning it is going to absorb energy. So the solute is first aggregated, it takes heat and the solute will become separated. So the delta H for that process is going to be greater than 0, positive. Step 2. Solvent particles also need to separate from each other. That process is also endothermic. Solvent aggregated, take heat and become solvent separated. So the delta H solvent going to be greater than 0. Now we have the separated solvent and separated solute. So the step 3 would be solute and solvent particles mix and form a solution. That step is exothermic. It releases energy. So the solute separated, solvent separated, become the solution and remove heat or release heat, and then delta H of the mixture will become less than 0. Okay, so we can see that in this diagram here, enthalpy component of the heat of solution, you can see here solute, first aggregated solute, take heat and become separated solute particles, and then the solvent, it's together first and then the solvent particles separated. Both of these processes are endothermic, so that's why you see energy is increased when they separated. Now these two are going to mix with each other, and then during that mixing process it releases heat. So now the energy is going to be less than where they started from. So the difference, heat absorbed and heat released. Heat released is more than the heat absorbed, so then it is a exothermic process. So finally you have a solution where the solvent and the solvent are intermingled with each other. So the exothermic solution process, delta H mixture over here is greater than the delta H solute and the delta H solvent, and then the delta H solution. Okay, the delta H solution is going to be at the end less than 0. Yes, we were correct. I was just a little bit confused with this terminology. So these two, delta H mixture is going to be greater than delta H solute and the delta H solvent, meaning these two together combined going to be greater than 0, but at the end delta H solution is going to be less than 0. Negative number would be for enthalpy and it will become endothermic process. Exothermic process. Delta H going to be less than 0. Exothermic process. In an endothermic process, again, in both cases, solvent and the solute become separated are going to be endothermic. It needs energy for them to be separated. You see, to absorb energy and come to a high energy state, absorb energy, come to a high energy state, then it started with. And then in endothermic solution process, once they mix, it doesn't release energy, it absorb energy. Okay, so it will stop somewhere here in terms of energy, delta H final. So the delta H for the solution is going to be greater than 0, positive value. This number minus this number will make it a positive value, which is for a endothermic solution process. Okay, the heat of solution, delta H solution equals delta H solute plus the delta H solvent plus the delta H mix. So delta H solution, so this is the delta H solute, delta H solvent, and then the delta H solution. Okay, so that determine the delta H of the solution, delta H mix. Delta H mix. I said delta H solution, but this has to be delta H mix. Okay, the overall solution process may be either exothermic or endothermic depending on the sizes of these amounts. It could end up being positive or negative. If the delta H solution become negative, that's an exothermic process. If the delta H solution become positive, that would be an endothermic process. So in exothermic process, delta H solution less than 0 because the sum of the endothermic processes, which is delta H solute, and the solvent is smaller than the exothermic term, delta H mix. Endothermic process, delta H solution going to be greater than 0 because the sum of the endothermic processes, which is delta H solute, and the solvent is larger than the exothermic term. Okay, so when you are mixing a solute and a solvent, it could either be exothermic or endothermic overall. Solvation and hydration. Solvation is the process in which a solute particle is surrounded by solvent particles. So the solvation is common to any kind of solvent. It could be water, or it could be alcohol, it could be an organic solvent. So in general, we call it as a solvation when the solute particles are surrounded by the solvent particles. If it happens in the water as the solvent, we call it as a hydration. Okay, so the delta H solvation equals delta H of the solvent plus the delta H mix. In water, delta H solution equals delta H solute plus the delta H hydration. Hydration of an ion is always exothermic because ion dipole forces are very strong. Meaning, if you are trying to dissolve anything in water, always that process is going to be exothermic. A positive ion in gaseous phase and the negative ion in the gaseous phase becoming positive ion in aqueous or negative ion in aqueous. Delta H hydration is always less than 0. Meaning it's going to be exothermic. Okay. Solutions and entropy. We learn about entropy, excuse me, when we talked about the second law of thermodynamics. So this entropy S of a system is related to the number of ways a system can disperse its energy and therefore to the freedom of motion of the particles. Gases have the highest entropy of the three states of matter. A solution usually has higher entropy than the pure solute and pure solvent. If you have a solution, they will have a higher entropy than the pure solute and pure solvent. Increase in entropy is favored in both physical and chemical processes. If there is a chemical process happens or a physical process happen, if the entropy is going to increase through that process, it always favor that reaction to take place. Solubility and equilibrium. A saturated solution contains the maximum amount of dissolved solute at a given temperature in the presence of undissolved solute. So if you have a saturated solution, you will have the maximum amount that it can dissolve that solute in that particular solution. Undissolved solute is in equilibrium with dissolved solute. If you cannot dissolve anymore after it becomes saturated, there are some solute undissolved, there are some solute dissolved, so they are in equilibrium. Unsaturated solution always has less than the equilibrium concentration of dissolved solute. If more solute is added, it will dissolve. Factors that affect solubility. Temperature affects solubility. If you have a very less solubility at room temperature, by increasing the temperature or giving heat, you can make that solid to dissolve in water. Most solids are more soluble at higher temperatures. Gases become less soluble as temperature increases. Gases become less soluble. They try to escape from the solvent that we try to make them soluble. Pressure affects the solubility of gases. Gases become more soluble at higher pressure. So if you give the pressure, the gas particles will try to go into the solution and increase the solubility. Effect of pressure on the gas solubility. You can see there are three types of pressures: pressure 1, 2 and pressure P1 and P2. Here P1 has a certain pressure. So you can see gas particles are in equilibrium with the solvent that it's trying to dissolve. What happens as you increase the pressure? As the pressure increases, more gas particles collide with the liquid's phase. More gas particles dissolve until equilibrium is re-established. So you can see these are going to soluble in the liquid phase. Excuse me. We can do Henry's law. So Henry's law tells us the solubility of a gas, given the term S gas, is directly proportional to the partial pressure of the gas above the solution. So if you want to find out the solubility of a gas, if you know the partial pressure of the gas, we can find out using this Henry's law equation. Here Kh is the Henry's law constant. It should be given to us in order for us to find out the solubility of a gas. Let's look at this with an example, also with the Henry's law constant. Using Henry's law to calculate gas solubility. The partial pressure of carbon dioxide inside the bottle of cola is 4 atm. So the partial pressure is given as 4 atmosphere. What is the solubility of carbon dioxide? We are given the Henry's law constant 3.3 into 10 to the negative 2 at 25 degrees, the same temperature with units also given. So we can use this Henry's law constant given, partial pressure of carbon dioxide given, so we can find out the solubility of carbon dioxide gas. Pretty easy. So solubility of carbon dioxide, Henry's law constant, which is this number, 3.3 into 10 to the negative 2 with the units, and then the partial pressure 4. So atm cancels. So solubility is 0.1 moles per liter. So you multiply these two, this number and this number. Quite straightforward, right? Okay, some concentration definitions. Then we're going to learn and do some examples with these ones. You guys know about the molarity. We did lots of molarity calculations in General Chemistry 1 also. The ratio for molarity is the number of moles of solute over the volume in liters. And then we're going to also learn something called molality. Look at here, it's molarity, but this one is molality, L, with the simple m or the small m. But the ratio going to be again the same for the number of moles, but the solvent is given in terms of kilograms instead of liters. And then we can also find out parts by mass. That ratio would be mass of the solute, mass of the solution. Okay, you can either use grams or you can use kilograms, but it has to be the same unit, mass of the solute over mass of the solution. And parts by volume would be volume of the solute, volume of the solution. Mole fraction, given the symbol X, would be number of moles of the solute. You divide by the number of moles of the solute and the number of moles of the solvent. Now with these definitions, let's look at some questions. Now this one is asking, what is the molality of a solution prepared by dissolving 32 grams of calcium chloride in 271 grams of water? Remember, the molality is moles, number of moles over mass in kilograms. So our solute is calcium chloride. Given in 32 grams, we need to convert grams into moles using the molar mass. Mass to molar mass, from the molar mass you calculate number of moles. And then you're going to divide it by water or the solvent in kilograms, converting 271 into kilograms. That will give us the molality like this. 32 kilograms using the molar mass of calcium chloride 110.98, convert to moles over solvent mass in kilograms, 271 over 1000, convert to kilogram. That will give us the molality. Next question, find the concentration of calcium in parts per million in a 3.50 gram pill that contains 40.5 milligrams of calcium. So we are going to find the concentration, but the unit need to be parts per million. In a 3.5 gram pill that contain 40.5 milligrams of calcium. Let's see how to do this one. First you need to do is convert milligrams to grams of calcium. So this is given in milligrams, 40.5. Convert milligrams to grams. And then find the mass ratio of calcium to pill and multiply by 10 to the power 6. Let's try to see how that's been done. First thing, 40.5 milligram convert into grams. 1 gram is 1000 milligrams. Okay, and then you divide it by 3.5 grams because this milligram contains in 3.5 gram pill. So you take this amount, convert to grams, you divide it by 3.5 grams. Okay, and then it has to be parts per million. If you take a million part, what's that going to be? So you multiply it by a million. Million is 10 to the power 6. So this needs to be 10 to the power 6, not 106. That's a typo right there. And this needs to be 10 to the power 4, not 104. So 1.16 into 10 to the power 4. So the parts per million is, if you remember that we did in our first experiment when we tried to find out the calcium hardness in water hardness in parts per million, it was grams per 10 to the power 6 parts per million. So that's the same thing that we are doing here. First you divide it by the amount 3.50 and then you multiply it by 10 to the power 6 to find it in parts per million. Okay. Okay. And then the next one, the label on a 0.750 liter bottle of Italian, how do you pronounce it? Shanti? Okay, you guys know how to pronounce it. Okay, you figure it out. The label on a 0.750 liter bottle of Italian indicates 11.5% alcohol by volume. So it has 11.5% alcohol by volume. How many liters of alcohol does the wine contain? The label on a 0.750 liter. So the size of the bottle is 0.750 and 11.5% is alcohol by volume. How many liters of alcohol does the wine contain? So how do we perform this one? We know the volume percentage is given to us, which is 11.5%. We also know the total volume 0.750. So we can find the volume of alcohol. Simple. Over here, the size of the bottle is 0.750 liter. And then we were given the percentage. Percentage means if you take 100 liters, 11.5 liters is alcohol. Right? So you take the given amount and use the percentage. So the amount of alcohol 0.0862 liters alcohol. Easy ratio. The last one. A sample of rubbing alcohol contains 142 gram of isopropyl alcohol. This is the formula. And 58 grams of water. What are the mole fractions of alcohol and water? Remember, the mole fraction is amount of solute, meaning the number of moles of solute, and you divide it by the number of moles of solute plus the number of moles of the solvent. Okay, so with that in mind, let's see how to answer this. Excuse me. We are given 142 gram isopropyl alcohol and also water. We want to find out the mole fraction of alcohol. So first we need to find the number of moles of alcohol, and you divide it by the number of moles of alcohol plus the number of moles of water. So everything is given in grams, need to convert to moles using the molar masses. Moles isopropyl alcohol 142 grams, this is the molar mass 2.36. And then the moles of water 58 grams, converting to moles using the molar mass 3.22. To find the mole fraction of isopropyl alcohol 2.36, you divide it by 2.36 plus 3.22 together. Like this. This is the mole fraction for alcohol. Number of moles of alcohol 2.36. You divide by the number of moles of both. 2.36 plus 3.22, 0.423. To find the mole fraction of water, number of moles 3.22, and you divide it by the total number of moles. Solute and the solvent together. Okay, and if you add these two together, this will give you 1 as the 100% mole fraction. Okay, to convert a term based on amount, number of moles, to one based on mass, you need the molar mass. We all know that. To convert a term based on mass to one based on the volume, you need the solution density, because the density is given as grams per milliliters. Okay. Molality involves quantity of solvent, whereas the other concentration terms involve quantity of solution. In molality, it involves only the solvent, but other concentration terms involve quantity of the solution. Okay, let's look at this example. Hydrogen peroxide is a powerful oxidizing agent used in concentrated solution, in rocket fuels, and in dilute solution as a hair bleach. Aqueous solution of hydrogen peroxide is 30% by mass and has a density of 1.11 grams per milliliters. Calculate the molality, mole fraction of hydrogen peroxide, and molarity. Remember, the molality is the number of moles over the mass of the solvent. To find the mass of the solvent, we assume the percentage is per 100 gram of solution. Meaning, when you say this H2O to 30%, if you take 100 gram of solution, 30 gram is hydrogen peroxide. Right? So then what would be the amount of solvent? 30 gram solute, 100 gram solution. So the solvent would be 100 minus 30, 70. Take the difference between the mass of the solute and solution for the mass of the peroxide to find the molality. Right? B, mole fraction. Mole fraction would be number of moles of H2O2. You divide by number of moles of H2O2 plus the water. We can do that too. And then the molarity again, number of moles over the volume. We can use the density to find the volume of the solution. Okay, easy. So the gram of the water would be 100 minus 30, 70 grams. This is for solution A. And then to convert to number of moles, 30 gram hydrogen peroxide, you divide by the molar mass of the hydrogen peroxide, that will give you number of moles. So to find the molality, you take this number of moles, you divide by 70, which is the mass of the solvent, and convert into kilograms, grams to kilogram. That will give you 12.6 molality H2O2. The next one is the mole fraction. We need to find out the number of moles. From the mass percent to mole fraction, 70 gram water, using the molar mass, you can find the number of moles of water. And then the mole fraction of hydrogen peroxide would be, we found the number of moles in the previous one, 0.882. You divide by 3.88, which is the number of moles of water, plus the number of moles of hydrogen peroxide, 0.185. And to find out the molarity, from the mass percent and density to molarity, we were given the volume of the solution. We are trying to find out the volume of the solution. We were given the mass of the solution, 100 grams. And then the density was given to us as 1.11. So 100 grams, use the density 1.11 gram, 1 milliliter. So this is the density. So to find out the volume, you use 100 grams and then use the density term, put in the grams into your denominator, keeping the milliliter in the numerator. So grams to grams cancel, convert into volume, 90.1 milliliters. Molarity is number of moles over the volume of the solution in liters. We found the number of moles, 0.882. You divide it by 90.1, convert into liters. That will give